In this video you will see how to solve the problems related to power series in case of an ordinary differential equation. So before going through the description, first of all we need to consider what are the possible definitions related to power series for the purpose of solving any problem related to power series. So let us start with the definition of ordinary and singular points. So what is the meaning of ordinary point? Any point, say x equals to x naught, is said to be an ordinary point of the equation y double dash plus pxy dash plus qxy, that is equal to 0 if both the functions px and qx are analytic at x equal to x naught. That means we are choosing a certain point x equals to x naught, and then we are trying to say when we can say it should be an ordinary point corresponding to this equation. Now the ultimate criteria is what? You need to consider both this function px and qx should be defined or analytic at the point x equals to x naught. Now it may happen at least one of them may not be defined at this particular point x equals to x naught. In that case, for this differential equation, whatever I have written, it can be considered as a singular point. So I am writing also this one, singular point, if the point x equals to x naught, say this is equation 1, whatever I have written, say the point x equals to x naught is not an ordinary point of equation 1, then it is called a singular point of equation 1. That means if px and qx both of them are defined, then we can say it should be an ordinary point corresponding to the equation 1, and if at least one of them is not properly defined, then you can say it should be a singular point. Now you can categorize this singular point into two types. First type of singular point is what? Regular singular point. Second type of singular point is termed as irregular singular point. Now, whenever we can say that the singular point x equals to x naught of equation 1 is a regular singular point if both x minus x naught into px, that means this particular function, and x minus x naught square into qx, both of them are analytic at the point x equals to x naught under consideration. I repeat, when we can say the point point is a regular singular point, as usual, first of all it has to be a singular point. That means it is not an ordinary point. Then you can say it will be a regular singular point if you can justify both x minus x naught into px and x minus x naught square into qx are analytic at the point x equals to x naught. And obviously you can understand from the definition, if any singular point is not regular, then you can consider it as a irregular singular point. Which is not a regular singular point can be termed as irregular singular point. So any singular point which is not regular is called an irregular singular point. Now, next task is what? How to determine the regular and irregular singular point using this definition. For example, let us consider the equation 2x square y double dash plus 7x into x plus 1 y dash minus 3y equals to 0. We have taken this differential equation. You can see, first of all, we have to compare this equation with the standard form y double dash plus pxy dash plus qxy, that is equal to 0. So this is the equation under consideration. So we can say y double dash plus 7x into x plus 1 divided by 2x square, then y dash minus 3 by 2x square into y, that is equal to 0. So this part can be written as y double dash plus 7 into x plus 1 by 2x into y dash, and then 3 by 2x square into y, that is equals to 0. Now say this is equation 1. Now comparing equation 1 with the standard form. What is the standard form? Y double dash plus px y dash plus qx y, that is equal to 0. We get px is what? Px is equivalent to this expression px y dash. So 7 into x plus 1 by 2x, and qx is what? This portion, as if it is the coefficient of y, we are choosing this one as qx, 3 by 2x square. Now suppose we are testing at x equal to 0. That means x naught is considered as 0 in my present example. So clearly you can understand, if you put x equal to 0, because of the presence of x in the denominator portion, both px and qx will be undefined. So if we take x equal to 0, then both px and qx are undefined at x equal to 0. That means they are not analytic at all. That is, both px and qx are not analytic at x equal to 0. Now remember, I told you, if the point x equals to x naught is not an ordinary point, then it will be considered as a singular point. And what was the criteria of becoming an ordinary point? It will be an ordinary point corresponding to this differential equation if both the functions px and qx are analytic at x equals to x naught. In this present example, we can consider x naught is 0. So here at x equal to 0, we have seen both px and qx are not well defined, or you can say they are not analytic at all. That means definitely x equal to 0 is not going to be an ordinary point. So you can say it is nothing but a singular point. So technically we can say, so x equal to 0 is not an ordinary point. Thus x equal to 0 is a singular point. Now immediately the question arises here, what type of singular point it is? I mean to say whether it is a regular singular point or it is an irregular singular point. So practically we need to check this criteria, x minus x naught into px. But as I told you, x naught is what? 0. So here you can see x minus 0 into px. Why I have written this criteria? Remember, x minus x naught into px and x minus x naught square into qx. If we can show both of these quantities are analytic at x equals to x naught, then you can see it will be a regular singular point. So here x naught is what? 0. So x px, this is the ultimate criteria. I hope we can remember what was the structure of px. X, and then we have px is what? 7 into x plus 1 by 2x, and qx is what? Minus 3 by 2x square. So here we need 7 into x plus 1 by 2x. So xx will be cancelled. 7 into x plus 1 by 2. Then let us find out this this part. Then x minus 0 whole square qx, that is x square into minus 3 by 2x square. So it will give you minus 3 by 2. So ultimately you have obtained these two quantities, and you can clearly understand both x minus 0 into px and x minus 0 square into qx, that means these two quantities are analytic at x equal to 0. So x equal to 0 is a regular singular point. It's a regular singular point. That means after obtaining the criteria of singular point, you need to verify what type of singular point you have obtained, whether it's regular or irregular. I hope this problem is clear to all. Now moving on to our next problem. Say we have taken 2 points. Show that x equal to 0 and x equals to minus 1 are singular points of x square into x plus 1 whole square y double dash plus x square minus 1 y dash plus 2y, that is equal to 0. So this is the differential equation under consideration. So you can write, given x square x plus 1 whole square y double dash x square minus 1 y dash plus 2y, that is it is equal to 0. Dividing throughout by x square into x plus 1 whole square, you will get this type of criteria, plus 2 by x square into x plus 1 whole square into y, that is equal to 0. Now say this is equation 1. Comparing 1 with the standard form, y double dash plus px y dash plus qx y equal to 0, we get this part is equivalent to px. So x minus 1 x plus 1 x squared x plus 1 whole square. So what is the final expression? X minus 1 x squared into x plus 1, and qx, this is equivalent to 2 by x square into x plus 1 whole square. Now if you put x equal to 0, then px will be undefined because of this x square, and also you can see qx is also undefined. So both px and qx are undefined at x equal to 0. Also, if you put x equals to minus 1, you can see another factor in the at the denominator is x minus x plus 1. So putting x equal to minus 1, this part will be 0. Similarly here this part will be 0. So here you can see at x equals to minus 1 also you can understand px and qx must be undefined. That means these 2 points are not ordinary points at all. They must be singular points. So ultimately you can say, so x equal to 0 and x equals to minus 1 are both singular points. Now we need to verify what type of singular points are there. Again, x minus 0 into px, let us find this one. Why? Because we are testing singularity at the point x equal to 0. So x minus 0 into px. So x minus 0 into px, pardon, I am, first of all we need to write, we are going to check the singularity at the point x equal to 0. We need a header here. After that you can write x minus 0 into px. Okay, so x minus 0 into px is what? First of all we need to write x minus 0 into px. We need to find out, sorry, x minus 0 into px is what? X, then x minus 1 x square into x plus 1. Now you can see x minus 1 by x into x plus 1. Again x minus 0 whole square into qx. This will be what? X square 2 by x square into x plus 1 whole square. X square into 2 by x square into x plus 1 whole square. So it will be equivalent to 2 by x plus 1 whole square. Now here, because x is present at the denominator, so you can see this part x minus 0 into px is not analytic at x equal to 0. That means you have obtained at least one expression between px and qx which is not analytic at x equal to 0, even after considering x minus x naught into px. Here x naught is 0. So you can say px is not analytic or well defined at x equal to 0. That is, it simply implies x equal to 0 is an irregular singular point. Irregular singular point. Remember the definition. If you can justify x minus x naught into px and x minus x naught square into qx, these two things are well defined or analytic at the point x equal to x naught, then the points can be termed as regular singular point. And if it violates any one of these conditions, then you can say it will be an irregular singular point. So here we have obtained x equal to 0 will be an irregular singular point. Again, let us verify at the point x equal to minus 1. The criteria is x minus x naught. X minus x naught into px. Here also you can make a header. We are testing at x equals to minus 1. So x naught is what? Minus 1. So this part will be reduced to x plus 1 px. That means x plus 1. And then we have this criteria, x minus 1 into x square into by x minus 1 divided by x square into x plus 1. So this part will be cancelled. So ultimately we have obtained this expression. So what does it mean? If you are putting x equals to minus 1, we can easily understand the function is well defined. So we need to proceed further. X minus x naught square into qx, that is x plus 1 whole square into qx. Remember what was the expression for qx? 2 by x square into x plus 1 whole square. So x plus 1 whole square into 2 by x square into x plus 1 whole square. So 2 by x square. Now you can see for both these expressions, At x equals to minus 1 we have no problem. So that is both x plus 1 px and x plus 1 square qx are analytic at x equals to minus 1. Here you should write x minus 0 into px is not analytic at x equal to 0. Okay, that means at x equals to minus 1 we have obtained a regular singular point, so it will be a regular singular point. So the idea is very simple. First of all, you need to identify the basic structure of the differential equation. That means whatever may be the structure, you have to compare it with the standard form y double dash, that is d2y dx2, plus pxy dash, that is px into dy dx, then plus qxy. After that you need to find out px and qx. Just observe the desired point, that is x equals to x naught. In different problems you will get different things. Then you need to verify what is the criteria of px and qx regarding analyticity, or whether it is defined or not at the desired point. If px and qx both of them are well defined at the desired point, or the point or at the point under consideration, then you can say the structure px and qx are analytic and simply the given point is an ordinary point. But if it is not so, then it will be a singular point. Already I have discussed singular point is of two types. There are two types of singular points. One is regular singular point, another one is what? Irregular singular point. Then you need to verify x minus x naught into px and x minus x naught square into qx for further proceedings. And then depending on the criteria, whatever you will get, you can justify whether it is a regular singular point or it will be an irregular singular point. Okay, so this is the first part of this expression. Now we are trying to see how to solve the power series whenever we are considering any ordinary point. So now our next topic is what? Power series solution. In powers of x minus x naught, or about the ordinary point x equals to x naught. This topic is very important in terms of examination point of view. Now it may not be written in the question that the given point is an ordinary point, so that's why we need to check initially whether it's an ordinary point or not. Then we need to proceed. Okay. So let me explain the given topic by means of an example. Say I am taking the example like this. Solve x square plus 1 in terms of power series obviously, plus xy dash minus xy equal to 0 in powers of x. If nothing is mentioned in the question in powers of x, that means you need to consider the point as x equal to 0. Sometimes it may be written about the origin or in the neighborhood of x equal to 0. Everything is same. Here in powers of x means you need to check about the point x equal to 0. Don't forget this one. Here I am writing also, you need to check about the point x equal to 0. Okay. Now given equation x square plus 1 y double dash xy dash minus xy equal to 0. Okay, please listen carefully now. This is the equation 1. Dividing by x square plus 1 we get, that means we are trying to get the standard form, y double dash plus x by x square plus 1 into y dash into this. Now you can compare this expression with the standard form. So comparing 2 with the standard form, like this, we get, what is the expression for px? X by x square plus 1. What is the expression for qx? Minus x by x square plus 1. Now here we need to consider the point x equal to 0. As I told you earlier, in powers of x is equivalent to this fact. So if you put x equal to 0 in place of px and qx, what will happen? Both these functions are well defined. So technically you can say here both px and qx are analytic at x equal to 0, and that means definitely it's going to be an ordinary point. So x equal to 0 is an ordinary point. So we have verified what type of points it is. So if it is not an ordinary point, then it will be a singular point. Then we have to use another technique that is called Frobenius method. Later we will discuss that one too, but right now let me focus on this particular topic, that is we are trying to solve the given differential equation in terms of power series about any ordinary point. What type of ordinary point is this one? X equal to 0 is the ordinary point under consideration. Now just observe carefully how to solve this problem. So let us consider the solution be taken in this form: y is equal to c naught plus c1x plus c2x square plus c3x cube, and so on. You can see this is an infinite structure, and obviously we have taken the structure in the form of a series. So in terms of summation notation, we can write this thing: summation c n x to the power n, where summation should vary from n equal to 0 to infinity. Say this is equation 3. As per our assumption, let this expression y is nothing but the solution of the given problem. I hope up to this clear. That means after checking whether the given point is an ordinary point or not, first of all you have to assume this is the general structure of the solution. Okay, so let y is equals to this be the solution of the given equation. Now let me write this one. Now observe the given expression. You have taken y is equals to like this, then you need to find out y dash as well as y double dash. Okay, let me show you one thing. I am writing here in terms of note. We have taken y is equals to c naught plus c1x plus c2x square, c3x cube, and so on. So if I find out the derivative of y with respect to x, you can see this is a pure constant, so it will be 0. So from here you will get c1, from here you will get 2c2x, from here you will get 3c3 x square, and so on. So if we express this structure by means of summation notation, what type of expression you can imagine? Here you can imagine this is x to the power 1. This can be imagined as 1 into c1 x to the power 0. So can we write this is equivalent to ncn, where n varies from 1 to infinity along with x to the power n minus 1. Okay, I repeat, ncn x to the power n minus 1. Put n equals to 1, you will get 1 c1 x to the power 0. If you put n equals to 2, you will get what? 2 c2 x to the power 2 minus 1. Similarly, putting n equals to 3, 3 c3 x to the power 3 minus 1. In this way we can carry on. So that means if y summation cn x to the power n, where n varies from 0 to infinity. In short, you can easily remember this thing by considering the normal derivative of this expression. Automatically it will give you n cn x to the power n minus 1. Only you need not to forget that summation should not be n equals to 0 to infinity in case of y dash, because the first term is already removed. So here you can say differentiating 3, probably I have taken this equation as 3, differentiating 3 twice with respect to x. We have taken successive derivatives actually. Y dash is written as n cn x to the power n minus 1, where n varies from 1 to infinity. Automatically y double dash will maintain the same format. N, here x to the power n minus 1, differentiate this expression. Cn, keep this one intact, x to the power n minus 2. Here number of terms will be decreased again, okay? So technically n varies from 2 to infinity. Now let me show you. This is the expression for y dash. Y double dash will be what? This part will be 0. C1 is a pure constant. This part will be 2c2, then 3 into 2 c3 x. If we consider one more term, that is c4 x to the power 4, then it will give you 4c4 x cube, then 4 into 3 c4 x square plus so on. So just observe this pattern. 2, 3, 3, 4, in this way you are considering. So n into n minus 1 cn x to the power n minus 2 I am taking, where n varies from 2 to infinity. Just put n equals to 2. Then putting n equals to 2, you will get what? 2. This is 2. 2 minus 1, 1. That is 2 into 1. That is simply 2. C2. C2. X to the power 2 minus 2. That is what? X to the power 0 equivalent to 1. So 2c2 first term. Putting n equals to 3. 3. 3 minus 1. That is 2. 3 into 2. C3. And then x to the power 3 minus 2. That is x. Putting n equals to 4. 4. 4 minus 1. That is 3. And after that c4 x to the power 4 minus 2, that is x square. So here you can see the abbreviated version can be written in this way. So say this is equation number 4. Now using 3 and 4 in 1, we get in 1 means, that means in the given differential equation. What was the differential equation? This one. X square plus 1 y double dash plus xy dash minus xy equal to 0. X square plus 1 into y double dash. So x square plus 1 y double dash means this one. Then xy dash, x y dash, n equals to 1 to infinity, n cn x to the power n minus 1 minus xy. Cn x to the power n varies from 0 to infinity. On the right hand side, probably it was 0. I think so. Yes, it is 0. So simply y double dash, y dash and y, all these values are used in the original differential equation. Now let us simplify. N into n minus 1 cn x to the power n minus 2 into x square. First simplify in this fashion. So it will be x to the power n, then plus n equals to 2 to infinity n minus 1 cn x to the power n minus 2. Then what is the next part? N equals to 1 to infinity n cn x to the power n minus n equals to 0 to infinity Cn x to the power n plus 1. Up to this clear, I guess so. Now here you can see we have obtained different summations. N equal to 0 to infinity, n equals to 1 to infinity, n equals to infinity. You have obtained different structures, and also you can see the powers are also different. X to the power n, x to the power n plus 2, here x to the power n plus 1, etc, etc. So first of all, try to identify the least possible power of x. Here x to the power n, here x to the power n plus 1, here x to the power n minus 2, in this way. Actually not least possible power, you can try to modify this expression so that you will get x to the power n in every possible structure. Try to modify this expression in terms of x to the power n. That means already in the first term you have x to the power n, so there is no need to modify this expression. But in the second term you have x to the power n minus 2, then x to the power n, here also it is perfect, here also x to the power n plus 1, you need to modify this expression. Okay, so try to adjust the power so that all possible structures will have the identical structure, like something into x to the power n. That means already we have x to the power n, I repeat, we need not to modify this one. But here you have x to the power n minus 2 converted into x to the power n. Here already x to the power n is there, no need to modify this one, but this term has to be modified. Now the question arises, how can you modify? First term, as I told you, no need to change, so simply write this n minus 1 Cn x to the power n. Now n minus 2, just imagine in this way, n minus 2 is right now to be replaced by n. Okay, so technically if we can replace n by n plus 2, n by n plus 2, then definitely this portion will give you what? X to the power n plus 2 minus 2, that is x to the power n. N minus 2, if you consider this one to be n, then what will happen? N will be n plus 2. That means whenever you have obtained n, in which expression you have obtained n, simply replace n by n plus 2. Automatically you will get the power as x to the power n. So just observe this one. This part will be n plus 2. This part will be n plus 2 minus 1. That is n plus 1. This one will be Cn plus 2. This one will be x to the power n. Now n is right now n plus 2. So n plus 2 will be 2. That means n will be 0 to infinity. So you can see summation is also changed. I repeat, this power n minus 2, x to the power n minus 2, will be converted into x to the power n. Think in this way first. So n minus 2 will be occupied by n. So n minus 2 equals to n. That means previous n is now right now equals to n plus 2. So whenever you have obtained n, simply it has to be replaced by n plus 2 for this term. So n has been replaced by n plus 2. N minus 1 is given by n plus 2 minus 1, that is n plus 1. Then Cn plus 2 as usual, x to the power n minus 2, it will be nothing but x to the power n plus 2 minus 2. So you have obtained x to the power n. And n varies from what? N is replaced by n plus 2. So n plus 2 equals to 2, that means n equals to 0 to infinity. Here also you can see, no need to change this one, n equals to 1 to infinity n Cn x to the power n, because I told you if you have x to the power n, no need to modify. But in this case again you need to change x to the power n plus 1. So that means right now imagine n plus 1 should be what? N plus 1 will be treated like what? N. So how can you modify? N plus 1 is equals to n. Think in this way, n plus 1 equals to n. That means n will be n minus 1. That means n should be replaced by n minus 1. So Cn, it will be Cn minus 1. X to the power n minus 1 plus 1, it will be x to the power n. And summation, in place of n, just put n minus 1. So n minus 1 equal to 0 to infinity. So that means n minus 1, 0 means n should be 1 to infinity. So this is your next part. Am I clear? So in this way you have modified the structure. So you can see everything is right now x to the power n into something, x to the power n into something, x to the power n into something, x to the power n into something. Now next task is to adjust the summation. You can see there are several types of summation, n equals to 1 to infinity, 0 to infinity, 2 to infinity. We cannot consider this different types of summation at the same time, so we need a parity. So how to consider this one? Identify from this particular expression the least possible summation. I repeat, the least possible summation. What is the meaning of least possible summation? If I say n equals to 0 to 5, what does it mean? N equals to 0 to 5 means n equal to 0, n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5. 6 terms are there. N equals to 0 to 5. N equals to 1 to 5 will be what? 1, 2, 3, 4, 5. 5 terms will be there. N equals to 2 to 5 is what? 2, 3, 4, 5. 4 terms are there. So which one is going to be the least summation? Obviously 2 to 5, because we have only 4 terms in that expression. Here also this is an infinite structure, but the summation starts from 0 to infinity. Here the summation starts from 2 to infinity. Here the summation starts from 1 to infinity. So 0 to infinity, this is the largest possible structure. Why? Because it will contain the 0th part, the first part. Here 0th part is excluded. Here 0th part and first part, both of them will be excluded. So this is the smallest possible summation. So try to express everything in terms of summation n equals to 2 to infinity. So first part, you need not to modify anything. That is summation n equals to 2 to infinity n into n minus 1 cn x to the power n. This is the first expression. Now put n equals to 0 in this expression. Putting n equals to 0, you will get what? 2 into 1, that is 2 c2. Then x to the power 0 is what? 1. Then putting n equals to 1, you will get n plus 2, that means 3. 3 into 2, because you are putting n equals to 1. 3 into 2, that is 6. Then n equals to 1 will give you c3. 1 plus 2, 3. And then x, that means you are using n equal to 0 and n equals to 1. And then you can write n equals to 2 to infinity as usual, because the remaining terms need not to be simplified. So n plus 2, n plus 1, cn plus 2, x to the power n, plus this part. Already I told you n equals to 1 to infinity. So putting n equals to 1, c1x plus summation n equals to 2 to infinity n cn x to the power n. And the final one, putting n equals to 1, c naught x plus summation n equals to 2 to infinity cn minus 1 x to the power n. So you can see I have split it, the larger summation, in such a way, first term, second term, then the summation will start from 2 to infinity. In this way I have considered all these expressions. Now separate all this expression in terms of their powers. That means 2c2 is a constant. You have to write this one initially. Then separate the powers, separate the terms, in terms of x. That is, you can see 6c3x, c1x and c0x with a negative sign. So 6c3 plus c1 minus c0 into x. This structure will be considered. And after that, finally you need to consider summation. And summation is what? Summation n equals to 2 to infinity n into n minus 1, then cn, this part, n into n minus 1, then cn, then n plus 2, n plus 2, n plus 2, n plus 1, cn plus 2, then n plus 2, n plus 1, cn plus 2. After that we have cn minus 1, and then here also we have another term ncn. So you can write this one as ncn minus cn minus 1 x to the power n. So this is the final structure. X to the power n is present for each of these terms. That's why we can write. So thus we have obtained a certain expression. Previously I have used equation number 4. So it will be equation number 5. Now definitely it is nothing but an identity. So we can consider this mathematical identity and we can find out the possible values of these constants right now. Now here you can see right hand side is 0. So that means there will be no part related to x, nothing related to x to the power n. So we can say, since equation 5 is an identity, so equating the constant term means on the left hand side we have obtained 2c2 and the coefficients of different powers of x to 0, we get, first we have obtained 2c2 equals to 0. That means c2 should be equal to 0. This is one possible expression because there is no constant term except 0. Then we have coefficient of x, that is what, 6c3 plus c1 minus c0. This part is also equal to 0. And the most important thing, for all possible n starting from 2, you can have this entire coefficient is equal to 0. So we can write n minus 1 cn, n plus 2 n plus 1 cn plus 2, n cn, cn minus 1. This part is equal to 0 for all n greater or equal to this, because the summation starts from n equals to 2 to infinity. So this relation is valid for all n greater or equal to. This is the most important relation of this problem, and this relation is called recurrence relation. From here you can relate the coefficients. Okay, so c2 is already 0. Now from the second relation, that is the coefficient of x, will look like this. Here try to identify the constant c3 in terms of c0 and c1. So two constants should be independent and other constants should be expressed in terms of these first two constants. I repeat, whenever you are solving this type of problems, always remember first two constants in general, c0 and c1, or whatever you can have as your first two constants, should be treated like an independent structure, and remaining all possible constants like c3, c4, c5, c6, whatever you may get, will be depending on c0 and c1. So c3 can be written as c0 minus c1 divided by 6. So this is another possible relation. Now from here try to simplify first if possible. So you can see n square minus n plus n, and then you have cn, n plus 2, n plus 1, cn plus 2 minus cn minus 1. This is equal to 0. So n square cn, n plus 2, n plus 1, cn plus 2 minus cn minus 1. This is equal to 0. So let us try to find out cn plus 2. Now again you may ask, why should we consider cn plus 2 here? Because here try to identify the largest possible suffix. Here you have n, here you have n minus 1, and here you have n plus 2. So technically the possible largest suffix is what? N plus 2 in this case. So always try to find out the constant in terms of largest possible suffix. That's why I need to separate cn plus 2 from all these expressions. So it can be written as cn minus 1 minus n square cn divided by n plus 2 into n plus 1. And don't forget, this relation is true for all n greater or equal to. And this is equation 8. This particular relation you can write equation 8 represents the recurrence relation. Okay, now don't forget this recurrence relation is unique. Don't take this thing. It is not unique at all. In different problems you will get different recurrence relation. Okay. Now, what is the utility of this recurrence relation? Already we have obtained C2 equal to 0. I told you everything should be obtained in terms of C0 and C1. So C0 and C1, these two things are independent. C3 is already obtained in terms of C0 and C1. Now, if you put n equals to 2, just observe, automatically you will get C4. So putting n equals to 2 in 8, you will get C4. Then on the right hand side you will get what? C1 minus n equals to 2, don't forget, so 4 C2 n square, that is 4 C2, divided by what will be the result? N equals to 2 means 2 plus 2 4, and then we have 3. But C2, what is the expression for C2? Already we have obtained 0. This part is 0, so C4 is C1 by 12. See, C4 is also attained in terms of C1. Putting n equals to 3, in this equation, C5, here you will get what? N equals to 3 means C2, that means 9 C3, divided by n equals to 3 means what? N, 3 plus 2 5, 3 plus 1 4. So technically you can obtain minus 9 by 20 C3. But don't forget, C3 is also dependent on C1 and C0. So you can write minus 9 by 20 into 1 by 6, C0 minus C1. So you can cancel. So ultimately we will get minus 3 by 40, C0 minus C1. Now in this fashion you can find out 3-4 constants maximum. So I am finding out one more. C6, putting n equals to 4. So C3 minus 16 C4, 4 square Cn, 4 plus 2, that is 6, 4 plus 1, that is 5. Now C3 is what? C3, C0 minus C1 by 6. So 1 by 30, C0 minus C1, this one, by 6, minus 16, C4 is what? C1 by 12. So here again you can solve 3, 4. That means 1 by 30, C0 minus C1 by 6, minus 4 C1 by 3. Now here you can simplify. 1 by 30, C0 minus C1 minus 8 C1, after taking LCM we will get this one. So C0 minus C1 minus 8 C1 will be the structure. So C0 minus 9 C1 by 6. C0 minus 9 C1 by 6 into 1 by 30, I guess. 1 by 30. So C0 minus 9 C1 by 180. So the result will look like this. C1 by 20, etc. So we have obtained few constants. Now remember, what was your solution? You have started from here. This is the solution of the given problem. Y is equals to C0 C1x plus C2x square plus C3x cube and so on. So let us put this. Now we have y is equals to summation cn x to the power n. Don't forget this. That means y is equals to c naught plus c1x plus c2x square plus c3x cube plus c4x to the power 4 c5x to the power 5 and so on. In this way we can proceed. So c0 c1, remember I told you no need to change these two constants, rather all other possible constants should be obtained in the form of c0 and c1. So c0, no need to change this one. C1x, here also it should be intact. C2, I guess you remember it is 0. C3, C2 is 0. C3 is what? C0 minus C1 by 6. What is C4? C1 by 12. What is C5? Minus 3 by 40, C0 minus C1. X to the power 5 plus dot dot dot. Okay. And if you want to write one more term, what is C6? C0 by 180 minus C1 by 20 x to the power 6 plus dot dot dot. This is the expression. We have obtained this one as C6. This one is C6, don't forget. So C0. Then let us separate everything in terms of C0 and C1. So C0, if we take common, this is 1. This is x cubed by 6. This will be minus 3 by 40 x to the power 5. Next term is what? C0 by 180 x to the power 6. So I am not writing this. You can identify the sign. Because I have obtained up to C6, you will be able to understand what will be the exact sign after this term. So here it is plus C0 by 180 x to the power 6. So I can write plus dot dot dot. Okay. So if you want to give your answer up to x to the power 5, you should calculate up to x to the power 6. Why? To understand what is the actual sign of the next term. If you want to give your answer up to x to the power 6, then you should calculate up to x to the power 7 to understand what type of sign or symbol should be used after your expression up to which you want to write. So here it is plus in terms of C0. And then in terms of C1 it should be what? First is x. Second one is what? Minus x cubed by 6, as you can see. Then x to the power 4 by 12, and here minus minus plus 3 by 40 x to the power 5. And if you see C1 by 20 with a negative, so here you cannot write plus, so it should be minus dot dot dot. Okay, so unless you find this term, you will never be able to understand what is the actual symbol you should write here. So y can be written as C0 into something, C1 into something. So this particular solution can be treated as required solution, which is the required solution about or near x equal to 0, where C0 and C1 are arbitrary constants. That means everything has been expressed in terms of C0 and C1, arbitrary constants, and this is the result. So this is one type of solution where we have obtained the power series solution regarding an ordinary point. And remember, don't forget, if nothing is mentioned, then always to take the point as x equal to 0, and after that you need to verify whether it's an ordinary point or regular singular point or irregular singular point. Already I have discussed how to check this one, and after that you have to find out the solution of ordinary point about this one. Okay, So I have shown you the solution technique about the point x equal to 0. Later on I will discuss the other problems too. Thanks for watching. I hope this video will be useful for all of you. Thank you.